isn't as much about, hey, let's learn something new, but it's also about, but we will learn something new. We will, obviously. With me, you always do. That's what you get. So, you see the little, is this fine with everybody? Can you guys see clearly? Yeah? All right. So, this I need to make smaller. All right. Move it there. I'm going to stop this recording and start another one. All right, on Zoom. Okay. All right, we have fewer people today. How come? How come not enough people showed up today? It's not fun. I'm very, very kind of like sad. You know, sad kind of life. Yeah, that way. I don't know why. But people are. Excuse me. So, let's begin. Let us begin. Shall we? By the way, we also won the cricket match today. Just in case anybody's wondering. Yeah, that was a good game. Good game. Good test match. Yeah, good test match. Once in a while we play well. The boys played well, you see. The boys did play well. Yes, they did. All right. Okay. So, what are we doing in Equilibria, right? Yeah. Let me show you some examples of equilibrium. Have you ever seen equilibrium in everyday life? Well, one of the earliest. Okay, so let me start here. I should be. So, yeah. Basically, what we're going to do in chemistry are two things. We're going to talk about reversible reactions. Reversible reactions. The reactions that can proceed in either direction. And then we're going to talk about equilibrium. Now, there are many reactions that can be made reversible. All right. One very common reversible reaction is water evaporating. You see, you have liquid water in the liquid phase, and if you add sometimes at room temperature, but definitely above boiling point, water liquid starts to become water gas, right? And this is what's happening when you make coffee, tea, especially tea on the stove, right? The water starts to heat, it starts to boil away. You can also take in the night, especially in the winters, in the summers, when the winters are really cold and the summers mein kya hota hai ki summer's hot water in the night cools down and becomes dew. So when you have dew happening, it's basically water vapor in the air condensing to become liquid. So liquid water can become steam and water vapor can become liquid water. So basically this change of state, and in many changes of state, the reaction is in fact reversible. Yeah. Now there is another reaction that is reversible. A reversible reaction, I'll give you another example. So this is one reaction that's reversible. Another reaction that's reversible is when you heat calcium carbonate. If you heat calcium carbonate over time, it becomes calcium oxide and carbon dioxide. If you heat it. And also, if you pass carbon dioxide gas over calcium oxide, over time, it becomes calcium carbonate. And what is a reversible reaction really? Basically, in one case, you had calcium carbonate becoming carbon dioxide and calcium. And those two were the products of reaction number 3 for us. And in reaction number 4, the products of reaction number 3 are actually the reactants of reaction number 4. So 4 is the reversible reaction of 3. And 2 is the reversible reaction of 1. There are many others also. One very popular one is that nitrogen and hydrogen can combine to make ammonia. But ammonia over time can also decompose to give nitrogen and 3 hydrogens. So these are examples, reactions number 5 and 6 if I call them. 5 and 6 are also, 5 is reversible and 6. So many times we don't write them like this. We can write, for example, this reaction or the above one in the form of calcium carbonate is reversible with calcium oxide and carbon dioxide. This bottom one, I can write it as N2 and 3H2. Instead of writing two separate reactions, we write the same thing and we can make the arrow pointing backwards. So why write reactions 5 and 6 separately? This is reaction 5 and 6 written together, but with this sign. This sign is a reversible sign. Some of you might say, well, that's an equilibrium sign also. And equilibrium reactions are a subset of reversible reactions. So there are certain reversible reactions which will form equilibrium, and we'll talk about that right now. We will absolutely, this chapter is all about equilibrium. I just have to give you a basic idea what reversible reactions are. So reversible reactions are when basically reactions that can proceed in either direction. So A and B can become C, or C can become A and B. So A and B can become C, or C can become A and B. That is a reversible reaction. Now, this is the only way to identify it if it's given to you. Otherwise, it's called knowledge. Over time, if you ever do chemistry long enough, which I don't think many of you will do for too long, more than A levels, but if you were to, you'll come across more real life reversible reactions, and that's okay. You could say one reaction which is absolutely essential in plants, which is reversible, and that's something that everybody should remember and learn, is also reversible. It is respiration and photosynthesis. If you remember, photosynthesis is 6 carbon dioxides and 6 waters becoming 1 glucose molecule, and I believe it was 6 oxygens. And respiration, the reaction of respiration in animals is glucose burning in oxygen, 6 moles of them, to forming 6 moles of carbon dioxide and 6 moles of water. So this is also a reversible reaction, you know. So this is how you would write that. Okay, 6 CO2 and 6 waters. 6 CO2 and 6 waters. So I would recommend everybody should know this one. This is the one reversible reaction that you should know of, that's carried out every day. Especially if you're going to study about environment, this is one that you should know of. The other one that you should know of is the first one I gave you. The one where water became steam and steam became water. It is one of the most useful reactions in life. You know, this is an equilibrium between water in the liquid state and water in the gas state. Is a reversible. All right. So these two you should know. The others they'll tell you about. All right. Any questions so far, guys? I was on a speed and I was like buzzing through. Any questions now? Yeah. The top reaction is photosynthesis and the bottom reaction is respiration. The blue reaction is what happens during photosynthesis, and the yellow reaction is respiration. Yeah. All right. Yeah. Thank you so very much. Can you guys just excuse me for 1 second, please? Please, thank you. Apologies, I'm back. Yes. All right, everything clear? All good? All good? Yeah? Manaf, you don't know what's going to happen? I thought you were where? What? Okay. He doesn't know. We're doing reversible reactions and then we're going to do equilibrium. Sorry guys. All right. Yeah. Okay. Oh, you were not there with the last few classes. You missed some really kick-ass stuff, by the way. No, man. Okay. School date, it's okay. It's okay. You'll catch up. Recordings are there. Okay. Now. Wait. Okay. Now, I've explained to you reversible reactions, and there's a very common confusion between reversible reactions and equilibrium. And the difference between equilibrium and reversible reactions is, I'm going to use a basic example to explain that. You see, I'm going to use an everyday example if you guys use staircases ever in your life. So, you see, if you were to use the staircase to go up and down, if you go up and down a staircase, let's say you go up a staircase, what would you call that? Sorry, what I call that? What am I saying? Yeah. Dude, I'm taking class right now. I'm not here to answer questions about A levels right now. Sure, go ahead. Yes. No, I set up the website. I'm sorry, guys. I'm going to answer this question. No, Abu Stank. I purposely set up the website to make sure kids fail. What do you think, son? What do you think I'm going to answer you? Obviously, like, dude. Yes, everything is there. I don't know, man. A brain is also... Yeah, you might need a brain, you might need how to solve questions. That would also be a prerequisite. I'm in the middle of live class right now, teaching O-level chemistry. I should really turn off these comments on YouTube, man. I'm sorry, guys, on Zoom. Ridiculous. Sorry. It's because I'm taking class right now. It's in the middle of class, something like that happens. It really kind of irritates me. I should not look at them. Sorry. I should actually just hide them from my face right now. Thank you very much. Okay? It is enough. It is enough. You can use YouTube. You can use that. You can use whatever you want. You will only know if it's enough. If you're understanding it, it's enough. If you're not still understanding my videos on those channels, then they're clearly not enough, right? Because by that definition, even a book is enough. But people don't understand a book sometimes. So I even forgot what I was saying. Really, 1 second. Okay. So just in the example of going from, let's say, ground floor of your house to, let's say you live in a house with 2 floors. Now, let's say you were sleeping upstairs. So in the morning, you're going to come down, Then over the course of the day, in the evening, you might go back up. So coming down is, that is one reaction. Going up is another reaction. Think of it like that. So if you can think of, excuse me guys, sorry. Yeah. My bad, sorry, sneeze came. I know I'm not using chemistry to explain this because I want to use a non-chemistry example to show you the philosophical difference between reversible reactions and equilibrium. And I'm going to go talk about staircases and escalators to explain you the difference. Now, if you're on a staircase, and you're going down in the morning and you're going to go up in the evening. One time you want to come down in the evening, go up in the evening. Let's say you're going out and you live in an apartment building. You want to go down steps in the morning and go up in the evening. Now, going down is going in one direction. Going up is going in the opposite direction. So going up and down are reversible reactions. So you could go from the first floor to the ground floor. That's in the morning you do that. And then in the evening, you are going back up. So you're not doing them at the exact same moment. You're going forward in the morning, and let's write that. So you go forward in the morning. I might even change the color of the forward arrow. So let's say the forward arrow is green and so you are going to go down in the morning, that's a different time, and you're going to go back up in the evening. And so going up and down is a reversible process. You can go from up to down or down to up. But on a staircase, you really are not going to do it at the same time, are you? I mean, you might want to, but you might just be crazy if you want to go up and down at the same exact moment. Even if you just go down and up, you might do that one after the other. You might do that literally after 10 seconds. Okay, I'll go down and I'll go back up as exercise. But at the same moment, you will not be doing it. So if you do one and then the other, or do the other one then the first, that is not equilibrium. It's just a reversible reaction. So here, going up and down is a reversible reaction. All right? Yeah. But that's different from, that's not equilibrium. That is just going up and down at different times. On the other case, instead of let's say instead of steps, you were using an escalator to go back up in the night. Okay, let's say use escalators to go back up in the night, but the escalator is shut off. So you'd have to walk up, right? So now you're walking up and the escalator starts moving. In that moment, if you are going up, and now I'm talking about, and I'm going to scroll down, because now I'm talking about an equilibrium. Because what I'm talking about is that moment you are going up an escalator, running up, but the escalator coming down. And what starts to happen is you start going, there could be a moment where you are moving as fast up on the escalator and the escalator is coming as fast down. And in that moment, somebody who's standing not on the escalator but somewhere far away, to him or her, your head would not seem to be moving, because the speed at which you are going up would be the speed at which the escalator is coming down. In that moment, imagine that's the case. And if the speed at which you're going up and something else is bringing you down is happening at this exact same pace, maybe it was 2 steps per second you're taking up and the escalator is coming down 2 steps per second. So you're going up 2 steps per second and it's bringing you back down 2 steps per second. So the rate at which you are increasing your height is also the rate at which the escalator is decreasing your height. So to the outsider, you just don't seem to be moving. Now that is that moment in a reversible reaction that even though you are going up and the escalator is coming down, the rate at which both of you are doing the opposite thing is equal and you are not changing. That, my friends, is equilibrium. It has to be happening, basically going up and coming down has to be happening at the same exact time. Going up, coming down, exact same time. And if you're not moving, that is equilibrium. Versus you going up and down at different times, that's not equilibrium. So basically, a reversible reaction might need different conditions for going forward and backward. For example, when you have water, liquid becoming gas, you might need to heat liquid to become gas, but you might need to cool gas to become liquid. So those might require 2 different conditions. Okay, so when things require the exact same condition, that's when sometimes reversible reactions can become equilibrium reactions, meaning the escalator and you doing at the same time. Do you understand this analogy? Noman, I'm so glad you did well. Ramesh needs another example. Ramesh, I'm going to give you chemistry examples basically. It's very hard to give you more real life examples. Oh, I can. Okay. Yes, Radha. Absolutely. There are a couple of more examples. Now, we'll take the physics example first and then a chemistry example. All right. I need to turn my air conditioning on. 1 second. Yes, Mesa. So the idea is reversible reactions may or may not be equilibrium, but there are ways to make certain reversible reactions in equilibrium. But if something is in equilibrium, it can only be equilibrium if it is a reversible reaction. Yeah. So now another example. What does it mean to be equilibrium? Remember one thing. Equilibrium means in a state of constant. So even if the guy was moving and the accelerator is coming down, it's in equilibrium. Because they are moving and nothing is happening, in chemistry we call that a dynamic equilibrium. But that's not the only equilibrium we know. There are many more equilibriums that exist. That, one example is when you were a kid, you probably have played this game, Seesaw. And people can sit in different times as fulcrum, the whole idea of fulcrum. Now in physics, we call these forces are in equilibrium. The turning effect of forces are in equilibrium. Why? Because it's not moving. Even though this person is exerting its weight down, and so is this person. It's not like they are weightless, but the bar is so still it looks like it is weightless. If they had weight, shouldn't they move? But they have equal weights or at least equal turning effects, so their net result cancels out. What's an equilibrium in chemistry? It is basically a reversible reaction happening at equal speeds where the guy doesn't seem to move. All right. A good example is, by the way, have you ever, and I'll give you another example for chemistry now. So you can actually call water evaporating as a chemical change. There is van der Waals forces being broken when water evaporates. Now, if you were to, in Pakistan and most countries, we love washing our washrooms. We like washing. If you take a shower in the shower, the area is going to get wet. Some of us will wipe it out, but some of the tiled walls will have water. But we know that if we were to leave the washroom, maybe a little fan turned on there, even if not, after a few hours, the washroom will become dry. Because over time, the liquid will evaporate to become gas. And no matter how much water we have, when rains happen and water collects, especially in places like Karachi, over days, weeks, but the water eventually will evaporate. But we also know that when you have containers, where water is, let's say you have a container of a glass and you have water in it. Over time, the water will evaporate, and you leave that glass there for a few days, it will eventually become empty. But if you had closed it completely, then it doesn't dry out. You've also seen that happen, right? And the idea there is that in a closed system, like a closed glass, you end up developing an equilibrium. Let me show that to you. So this is an open system, for the lack of a better word. You got water in it. Obviously, I've taken it from another book, so the water was blue, inverted to become red. So this is water, and over time, it's evaporating more than it's condensing. And over the days, the water will evaporate out of the system. Even though the reaction is reversible, it's still not in equilibrium. But if you were to put a lid on it, what happens due to physics and due to concentration? What starts to happen, and we'll talk about that part later, we don't care about that right now. What happens is when you close the lid, you force over time the condensation and the evaporation and the condensation to happen at the same rate. So in an open system, the evaporation which is forward is having faster rate than the backward. And we've done rates of reactions. So a reversible reaction can have different rates. The liquid to gas evaporation is happening faster, while the gas to liquid is happening slower in an open system. In a closed system, very early on, you will come to a point where the speed or the rate at which liquid is becoming gas or evaporation is exactly equal to the gas becoming liquid. It doesn't start out that way, but over time it happens. And at that moment, you have made a what we call a dynamic equilibrium, because they're still evaporating and condensing, but the rate is equal, just like you were moving up an escalator. It's with as equal rate to the escalator coming down, so it seemed like nothing was changing, and the water will stay in the system and not evaporate. That's the idea of, basically, that's why we literally close the lid on any liquid. The moment you close the lid on any liquid, what you're doing is you are forcing an equilibrium between condensation and evaporation, and that's what we're going to work with. Okay, understanding that idea. Let me show that one example to you more. Like this was the idea that if you were taking a jar and the jar is closed, then the evaporation rate and the condensation is happening at the same speed, at the same rate. You open this jar and evaporation will start happening at a faster rate than condensation, and then we will not have an equilibrium anymore. It's because of this cork or lid is that we have maintained an equilibrium between evaporation going forward and condensation going backward. That's what we've developed so far. All right. Any questions so far about this? Are you following what I'm doing? It won't decrease or increase. Yes, Ramesh. Abso-freaking-lutely, Johnny. Absolutely. What do we have? Yeah? All clear so far? Yes. Okay. Now, okay. Okay. Let me show this to you. So now, this chapter can only be done after rates is done, right? Because only then can you understand it. So, let me just show that to you. So, okay, no questions, no questions, no questions. All right. Okay. Is osmosis and equilibrium? No. All right, what was I? Okay. Now, I'm going to show you a graph that will not be in your syllabus, okay? But it quantifiably explains to you what's happening in terms of rate. Now, you've done reactions and you've done rate calculations, you know, product with time and the rate is the gradient and that kind of thing. The basic graphs, right? For rates of reactions earlier. So, if I were to tell you that I have mathematically, I'm going to make a graph of not concentration but rate. So, basically, if you think about this, that if the reaction has two sides, the forward and the backward, okay? So, let's say I've got A becoming B. So, one is the forward reaction and the backward reaction. Now, what happens anytime you want to start an equilibrium? This is when you want to start an equilibrium. Like you put water in a glass and you put the lid. Initially, the water is evaporating, but its rate of evaporation slows down. This graph is the value of the rate. So, something might start off from a very high rate, but it starts to slow down. And as water starts to evaporate in the beaker, the backward reaction or the reverse starts to increase. And when the moment the rate of the forward and backward reaction become equal, not zero, equal, we say the equilibrium has reached. Now in a normal reaction, you need to understand this, that a reaction will stop eventually. Reaction rate will become zero the moment a reaction stops. But in equilibrium, the reaction never stops. It seems to have stopped. Like things will not seem to change because they are changing back and forth at the exact same rate. So there's no longer any net change, but the reaction continues to happen. And that's why we call it a dynamic equilibrium. And you're asked to learn the definition of a dynamic equilibrium. And so what is a dynamic equilibrium? And I will write it for you. A dynamic equilibrium is a state or a position in a reversible reaction when the rate of, because the reversible reaction has both a forward and a backward. So you should learn this. It's a state in a reversible reaction, therefore it has forward and backward, where the rate of the forward reaction exactly equals the rate of the backward reaction. Okay. And if you want to add more, there is no change in the concentration of reactants and products after equilibrium. There is no change whatsoever. And we'll be doing a lot of calculations for that in A levels if you study this in A levels. But you in O levels, we don't. We just try to understand what is a dynamic equilibrium. Any questions so far for this? Absolutely, Laiba. It is absolutely necessary. Yes. 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 Mm-hmm. Okay. How are they going to ask a question? Very basic. Define a equilibrium. The funny thing is, that's why, because they don't ask too much, kids end up just learning the definition and a couple of other things. And because they don't understand the idea of equilibrium, it haunts them, or at least because equilibrium is the one chapter that is very popular in second year chemistry in A levels. And in AS also level, there's a big chunk of it there. So, might as well want to fix it initially and then one go earlier on. All right? Okay? We'll worry about what they ask a little later. Yeah? Okay. Now, okay. All right. 1 second. Okay. What else? Okay, I'm not done yet, obviously. I'm continuing. 1 second. I'm just thinking what more to add to this. Am I skipping something? Yeah, 1 second. Yeah, I had some diagrams to send you. 1 second. All right. Okay. Could you please explain exactly what means the forward reaction rates? No, the forward and backward are not equal. Their rates are equal. They're not equal. Their rates are equal. Their rates. Their rates. Let me okay. How do I explain this? Okay. So if you want actual molecules to understand this, let's say your reaction was when a green A reacts with a blue B to make a product, a pink AB. So I've got A and B as my reactants make B. Now if this was not in equilibrium, it will go to completion. But I'm telling you that this reaction is reversible and eventually it will reach an equilibrium. So what does that mean? What it means is if I initially take A and B, all you have in the system is A and B, right? So, what you have is A and B only reacting. And I'll show that to you also right now. I'm just pasting that diagram here. And then bringing that up. So this might be a container where you just mixed A and B in together. So now the point is that initially maybe 3 molecules of A react with 3 of B momentarily. Then the next second, because you see, if you remember, rates depend on concentration. So the reason why you need to understand is that, and this is where rates of reactions come in. Initially in the first second, the rate of A and B reacting to go forward is the highest because they're the most amount of A's and B's. But then after 1 second, let's say 3 of A's react with 3 of B's. So let's say 3 of A's will react with 3 of B's to make 3 of AB. In that first second, let's say, I'll say, and this is me using fake numbers, but to explain to you mathematically what's happening. So in the first second, ye ho gaya. Now, in the second second, now, because you have used up A and B, their concentration in the second second is decreasing. Like imagine you literally have thrown away 1 second. You have reduced 3 A's and 3 B's. They're gone away. They're literally gone from here. And on the other hand, you now have some A's and AB. So now, if you forget AB for a second, do you now see after 3A and B reacting away, their amount has decreased? So if the amount has decreased, in the next second, the rate cannot be the same. So if the rate initially was 3 molecules per second, the rate might decrease to, let's say, 2 molecules per second. Get it? 2 molecules will react with 2 to make 2. But now, what's not just this, but before this happened, there were also 3 ABs. AB, AB, AB. And they start reacting too. And maybe in the same second, one of them becomes A and B again. You see, first, let me say this. The 3 of A and 3 of B became AB. And the second, because they have now decreased, only 2 of them in the second become AB. But since there is some AB, maybe 1 of AB becomes A and B again. So meaning now one of these guys is lost, right? And you get 1 of A and 1 of B back. Do you see that? So now I have more of A and B basically left. What am I doing? I had to first remove the 2, right? I didn't do that. So I had to first remove the 2 and basically I'll just remove them now. So I'll just remove two more A's and B's. Let's say A and B gone, A and B gone, right? So now two would lost, but we got two of them back from here, right here. So but still A, B's are now becoming even less. So in the third second, let's say what happens is, in the third second, because you have, sorry, what was it? You had three becoming, first there were three, one of them became this, but there was still two, we forgot the two. So there were two more ABs. And maybe in the third second, what starts happening is only one of A and one of B become AB, but in the same moment, only one of AB become one of A and one of B again. Okay? So what starts happening is at the third second, one of A and one of B are becoming AB, but also one of AB is becoming one of A and one of B again. In that moment, the rate at which you are making AB is 1 molecule per second. That's the rate of the forward reaction. Mathematically, it becomes 1 molecule per second. While it was 3 pehle, then it was 2, now it became 1. And the backward went from 0 to 1. So now at the third second in my example, dynamic equilibrium has been reached. It was reversible in the second second, but not equilibrium, because the rates were not equal. The first second it was 3 and backward was 0. So it was 3 versus 0, then 2 versus 1, and the third second it finally became 1 versus 1. And then what happens in the fourth second? Trust me, fourth second kya hoga? 1 1 becomes 1 and 1 becomes 1 and 1. And this keeps on happening and happening and happening and happening till the end of time. So 1 plus 1 will become 1, but not 1. It will just be going, it's like you give me, I give you, you give me, I give you, you give me, I give you. That's exactly what's happening at the molecular level. So what happens is over time, you're not even going to see much change, right? So eventually, like I said earlier, so you are going to be left at a certain amount and that will never change anymore. I'm so glad this made sense to you guys. I'm so glad. Hallelujah. I'm glad you guys liked it. Awesome. Yes, is the idea, understand, is that it is all about rate. It is rate. It's like two things happening together. The rates are changing, but they are changing of the forward and backward, and they're independent. But because they happen to be forward and backward, and the rate is becoming equal eventually, then it looks like, oh, it has stopped changing, but it is changing. Thank you, Alicia. Thank you. Yeah, you are. Thank you. I'll take a bow. Yes. Awesome. All right. So, yeah. Anyways, so now this. So this example, you could say that the rate of the forward reaction. So see, the rate of the forward, like if I were to make a graph, right? It came from 3 to 2 to 1. After the first second, it was 3. So basically it started off from 3, then it dropped to 2, then it dropped to 1. And the backward side started from 0, became 1 and stayed at 1 like that. And at that moment, that's what the graph was earlier. This was that graph right here. 3, 2, 1, 0, 1, and now they're equal. 1 molecule per second reacting continuously for the end of time. And this is what we call a dynamic equilibrium. All right? All righty. You're welcome, guys. Now, tomorrow, because I'm going to do the factors that affect equilibrium positions. But one thing I want to finish before tomorrow. Okay? One thing before that. So the rates do become equal. The rates become equal and the reaction continues to happen. But if I tell you what's the net yield, you see, because it made 3 first and then 2 more, but it removed 1. And then it kept making 1, removing 1, making 1, removing 1. So 3 plus 2, then remove was 1, you got 4. And so even though you might have 10 and 10, because 10 and 10 should have made 10, but only made 4 at the end, because after it the rate became equal. So in this particular case, you were supposed to make 10, but you only made 4. So we have a term called yield, and you are never going to get 100% yield, because you'll never going to make the product completely. It will never be formed completely. Neither will you have 100% product, neither will you have 100% reactant. The yield will be somewhere in between. In some reactions, it is, more reactants, less products, and in some cases, it's less reactants, more products. But that's something that I'm going to visually show you what I mean. I mean is that, okay, one second. Yep. Let me scroll down. I pasted the diagram. So basically, so if there is not equilibrium, 100% reactant will become 100% product. And this would have lied right here, the yield. Let's say this is the yield marker. Currently, this looks like about 30% yield. Okay, because only about 30% of the reactants became products, if you can think of it like that. And sometimes you're going to have reactions where it's the more product and less reactant, and you have to also be able to judge that, and they'll tell you. You just have to know that this is happening. All right, they will tell you that. And so you can also have this. So these could be two different reactions I'm giving you. Either you have, let's say this is about, I'd say 35% yield, while this is about 80% yield. So what it means is that before equilibrium was established, 80% of the reactants had become a product. Here, just at the point of equilibrium, only 35% had become. In my example, out of the 10 molecules of each that we had, we could only make net 4 ABs, because the reaction kept moving back and forth. So in our example, the yield was 4 out of 10 or 40%. Now obviously it won't be as simple as this, but I'm telling you that's how you get yield. It's that, okay, however much formed before equilibrium was achieved, where over what would have formed if there was no equilibrium. All right, and so equilibrium reactions will never have 100% yield. It will have less than that, and they will tell you sometimes if they need to tell you that. All right, and the real life examples in the real world, there are many reactions that are equilibrium, and what we want to do in the real world is either increase or decrease yield. That's our purpose in many chemical engineering ideas and in industries, to increase the yield basically of reversible reactions. All right, so I'm going to end this lesson here. In the next one, we're going to talk about all the factors that not only change rate but also have an effect on this idea, the yield, how to get more or less product. Show us what, Ramesh? I don't know. Oh, my face. He wants to see my face. Okay, Ramesh, you get to see my face. Where is my face? Here you go. This is my beautiful face. You see my face? Okay. Yes, here you go. This. He wants to see me face. I don't know what he wants to see me. Yes, because I had turned it off. I had turned the face off. And now it is back. This is back. All right. I hope you had a good time in class today. I absolutely did. This was so much fun teaching you guys. All right. Okay. What's wrong? Yes, Rafe does. Which song? What song are you talking about? Somebody's saying cringe. No offense. We can't, Lord. We can't. No, I forgot. No, man, I have no idea what you said. No, we can't for. Cringe. I have no idea. I've not paid attention. So maybe I forgot what I was saying. I loved it. And thank you guys. Thank you, Farwa. Thank you, Laba, Arisha, Noman, everybody, Ramesh, and Hanan, and whoever else showed up today. Mesam, Ramesh, Rida, Rahim. All right. And yeah, so I shall see you tomorrow, because what else will you do at 6 p.m. but hang out with me, right? Anyways, chalo, I'm see you guys later. Bye bye.